The horizon problem results from the premise that information cannot travel faster than light. In a universe of finite age, this sets a limit, the particle horizon, on the separation of any two regions of space that are in causal contact. The observed isotropy of the CMB is problematic in this regard. If the universe had been dominated by radiation or matter at all times up to the epoch of last scattering, the particle horizon at that time would correspond to about 2 degrees on the sky. There would then be no mechanism to cause wider regions to have the same temperature. U200A 191-202, U200A resolution to this apparent inconsistency is offered by inflation theory, in which a homogeneous and isotropic scalar energy field dominates the universe at some very early period before baryogenesis. During inflation, the universe undergoes exponential expansion, and the particle horizon expands much more rapidly than previously assumed, so that regions presently on opposite sides of the observable universe are well inside each other's particle horizon. The observed isotropy of the CMB then follows from the fact that this larger region was in causal contact before the beginning of inflation. U200A 180-186, U200A Heisenberg's uncertainty principle predicts that during the inflationary phase, there would be quantum thermal fluctuations, which would be magnified to a cosmic scale. These fluctuations served as the seeds for all the current structures in the universe. U200A 207, U200A inflation predicts that the primordial fluctuations are nearly scale invariant and Gaussian, which has been accurately confirmed by measurements of the CMB. U200A 66, U200A IF inflation occurred. Exponential expansion would push large regions of space well beyond our observable horizon. U200A 180-186, U200A related issue to the classic horizon problem arises because in most standard cosmological inflation models, inflation ceases well before electroweak symmetry breaking occurs. So inflation should not be able to prevent large-scale discontinuities in the electroweak vacuum. Since distant parts of the observable universe were causally separate when the electroweak epoch ended,